See Andrew nor Colby. I see the rest of you. So we're going to continue talking about thermodynamics concepts. So we ended before the break talking about temperature. We'll pick up talking a little more about temperature here. At least my recollection is that's where we ended. It has been, a week. So just reviewing about temperature. What is temperature fundamentally telling us about something? Let's make it simple. Let's say I have air. Air is pretty close to an ideal gas, which makes everything exactly what I said. If I have hot air versus cold air, what's really the difference between the two boxes of air? How fast the particles are moving. Which one's moving faster, the hot air or the cold air? The hot air is moving faster. Temperature is a measurement that's proportional to the average kinetic energy. And since kinetic energy is 1/2 mv squared, that means as temperature goes up, that v squared is moving up. So you double the temperature, the v squared doubled, which actually means that the speed went up by square root of 2, about 1.4 times faster if you double the temperature. Of course, what does double the temperature mean? If it is, let's say 30 degrees Fahrenheit, which is a chilly temperature, and then it becomes 60 degrees Fahrenheit, which is a little bit colder than we like, would you say the temperature doubled? Denford's nodding yes. Why do you nod yes, Denford? It's a very logical reason to nod yes. Yeah, well, 60 is 2 times 30, right? But there's different temperature scales. There's not just Fahrenheit. There's also Celsius. If we had put those in Celsius, we would have gone from about minus 1/2 degree to positive 17 degrees. Does that look like a doubling? No. So there's something a little bit interesting about this, that what does it mean to double the temperature is not as clear as one would have originally thought. So let's talk a little bit about the temperature scales. Oh, one more thing on this. Temperature is a measurement telling us how fast particles are going. It also tells us the direction that heat is going to flow. Heat always naturally goes from the hotter thing to the colder thing. So I talked about, I touch something, if it feels hot to me, that actual sensation is the heat, the thermal energy flowing into me. And since it flows from higher temperature to lower temperature, that means the thing I touched was a higher temperature than me. If I touch something that feels cool, what I'm actually feeling is the heat flowing out of me, which means that I was hotter than it. That goes along with this picture here. Let's talk about the temperature scales then. I should have changed the aspect ratio on this slide, or on, not the slide, but the equation. But two common temperature scales are the Celsius scale and the Fahrenheit scale. I talked about Anders Celsius original scale, didn't I? Did I not? Well, because he's a good Swede, I'm a quarter Swedish, an eighth Danish, and an eighth Norwegian. Put it all together, I'm half Scandinavian, right? So, Celsius came up with his temperature scale in 1742. Whoa. There we go. 1742, which is about 18 years after Gabriel Fahrenheit came up with his temperature scale. Fahrenheit's temperature scale, at least according to common legend, used 0 degrees as the temperature of frozen ocean water. That is, frozen ocean water means you have a combination of ice and water. And so at the temperature where ocean water freezes, where you have ice and water together, He said that's 0 on his scale. And then 100 degrees, my favorite joke here. I have a textbook that I used in graduate school, Callan was the author, that said that he used the basal body temperature of his wife for 100 degrees. So body temperature of his wife. Now I found other sources that say that it was the body temperature of a bovine that he used. And then, of course, I make the totally inappropriate joke of, yeah, like there was a difference. There's obviously a big difference. But he used 2 temperatures to come up with this scale. What's the difference between those 2 calibration points? 100 degrees. So we would call this a centigrade scale because it was 100 degrees between the 2 calibration points. Now, good old Anders Celsius said, I'm going to come up with a better scale. What's going to be better about it? I'm going to use better calibration points. So he used the temperature of boiling water to go along with his upper, and the temperature of freezing water to go along with his lower. What's the difference? They both had freezing water, but with Celsius, he used pure water. Anywhere in the world, you can go through a process and purify water and have the same starting point. Whereas the ocean water depends on the compounds, what salts you have and what other impurities you have, what its freezing temperature is going to be. So the pure water is a more reproducible reference point. Now, one thing that Anders Celsius did that virtually no one knows is he said, the temperature of freezing water I'm going to call 100 degrees. And the temperature of boiling pure water at 1 atmosphere pressure I'm going to call 0 degrees. So with Celsius' scale, the numbers went down as things got hotter. When Celsius died, then everybody said, well, that's ridiculous, and they flipped it over. And so the scale that we know as the Celsius scale is actually flipped from the one that Celsius developed. There's actually more to it than that as well. His scale was also a centigrade scale, 100 degrees between the calibration points. It's no longer a centigrade scale. The switch from Celsius being centigrade to Celsius not being centigrade occurred actually when I was in grade school. So it's, shall we say, recent? I like to think so. Now, instead of using that freezing point of water as the calibration point, the true calibration point that's used in the Celsius scale is 0.01 degrees Celsius is equal to the triple point pressure, or triple point temperature of pure water. And first of all, you say, well, 0.01 is very close to 0, right? But there is a reason why they switched to that. The triple point is a very specific point. There is only one combination of temperature and pressure where you can have water exist as a gas, a liquid, and a solid all at the same time. So, I mean, you can have 2 phases, we call these different phases, like water and ice, they coexist at 0 degrees Celsius. Water and steam coexist at 100 degrees Celsius, but water, steam, and ice all coexist at 0.01 degrees Celsius and a very specific pressure. When I said these other ones, you have to be at 1 atmosphere pressure for those temperatures to be the right ones. So this one here is even better because it's very, very specific. But that makes this a 99.99 grade instead of a 100 or centigrade scale. So those are the 2 common scales we use. Now converting between them, such as what you're going to do in lab today, is really quite simple. If you use the calibration points that Celsius originally used, there's 100 degrees between 0 and 100 degrees. Really, there's 100 degrees between 0 and 100 degrees. Between the freezing temperature and the boiling temperature of pure water at 1 atmospheric pressure. If you look at the Fahrenheit scale, the Fahrenheit scale has been recalibrated to using the same calibration points as the Celsius scale. So we no longer worry about, what's the composition of this, water that freezes, and what's the body temperature of a person. Those were not very reproducible. They were not good calibration points. So it's now just tied to the same standards as the Celsius scale. And so if you go from the freezing point of water in Fahrenheit, that's 32 degrees Fahrenheit, because it's used as a reference point, that's exactly. The boiling temperature for pure water at 1 atmosphere is 212 degrees Fahrenheit. So if you take the difference between those, it's 180 Fahrenheit degrees between freezing and boiling. It's 100 Celsius degrees between freezing and boiling. So that means that the ratio of the temperature change is 180 Fahrenheit to 100 Celsius. 180 divided by 100, drop off the last zeros, 18 divided by 10, divided by 2, 9 divided by 5. So the ratio of temperature changes is 9/5. So that's where we get the 5/9 or 9/5 here in the conversion equations. And then because 32 degrees Fahrenheit is 0 degrees Celsius, if you're going to go from Fahrenheit to Celsius, you take the temperature Fahrenheit minus 32. So at 32 degrees Fahrenheit, you have 0. Whereas if you're going from from Celsius to Fahrenheit, after you've done the 9/5 multiplication, you have to add the 32 back in. So the conversions are really quite simple between Celsius and Fahrenheit. One thing that I like about, I'm a scientist. As a scientist, I hate the fact that we use miles and that we use pounds. We never even talk about slugs, right? Slugs are the unit of mass in the imperial system. Nobody says, you, sir, have a mass of 37.5 slugs. But we could. One of the nicer things about the Fahrenheit, at least there's some positives about it, is that a Fahrenheit degree is a smaller change in temperature than a Celsius degree. So the difference between, 68 and 72, that's 4 degrees difference. And I tell you, my comfort level changes extremely in those 4 degrees difference. But in Celsius, that would be going from, 19.7 to 20.2 or something like that. It's not nearly as big a change in Celsius, so it seems like you're basically 20 degrees both ways. Actually, 68 is 20. So it's going from 20 to 20.5. But it makes it so you only need 2 digits to describe the temperature, and it's more precise. That said, I still wish we were like the rest of the world and using the Celsius scale, which is a simple, very close to centigrade scale. But I just went through these and talked about doubling the temperature. Neither of those really, they don't agree with each other if you're trying to double numbers to what's doubling the temperature. And it turns out that there is an absolute temperature. I should point out Celsius and Fahrenheit are the same at minus 40. Great physics joke for only nerds, and it's not funny at all. Man, it's so cold, it's minus 40. Celsius or Fahrenheit. And then we all laugh and laugh because it's the same. It's Celsius or Fahrenheit, you don't have to say. Okay, so, see, you guys are not laughing. So there's certainly something wrong with you. You can get colder than 0 Celsius. You can get colder than 0 Fahrenheit. Obviously, minus 40 is colder than both. And you can't get slower than stopped. So there has to be... Go ahead and answer this. Is there such a thing as an absolute 0? An absolute lowest temperature you could possibly reach?
Okay. We have 2, 0, 0, 2, 4. I will finish now what I was starting to say when I realized that I had a clicker question on the topic I'm starting to explain. Denford said that temperature is a measurement telling us about how fast things are moving. And things could go super, super fast. There's no upper limit until you get to relativity on speed, but it turns out that you have to redefine what temperature means. There's some weird things there. But there definitely is a minimum for speed. The slowest you can go is stopped. Once you're stopped, if you start going backward, you have a positive speed. It's just your direction that's changed. So there definitely is a minimum speed. And the temperature is proportional to the speed squared. Then that means that there must be a minimum temperature where everything has come to rest. And so we call that theoretical temperature absolute zero because it's the lowest you can possibly get. So the correct answer is yes. There is an absolute zero, and if that absolute zero exists, it doesn't matter what scale you're using, it's still going to have, this is the lowest you can possibly get. Now I have to point out just a technicality. Quantum mechanics throws a wrinkle into this. Quantum mechanics says that even at absolute zero, it's not possible to have things not moving. The ground state energy, the lowest energy possible for a simple harmonic oscillator. Now, this is kind of bizarre. If you're on a swing, quantum mechanics says you can't be stopped. You have to be doing oscillations back and forth. They're just really tiny so that we can't tell we're moving. If you get something small enough so that it is like an atom that is bound by atoms on the side, so it's like it's a little mass on a spring, that mass can't ever stop. It has to vibrate a little bit. So quantum mechanics says that you don't have an absolute zero where there's no motion because no motion is not possible. That's a technicality that we won't worry about. So how do we learn anything about this absolute zero? Well, we can do some simple experiments. You have a container here that's filled with gas. And you put it in water and you heat up the water. And as you heat up the water, what's going to happen is you increase the temperature. What's going to happen to the gas when you increase the temperature? It expands. So that gas expands. And so you can measure the volume of the gas as a function of temperature. And so you use different temperatures and you have different volumes. Well, if you have the volume expands when you heat it up, and when you cool it, what happens to the volume? It shrinks. But of course, there's a minimum value to volume. Right? The volume can never get smaller than zero. And so you can make a graph, and I think I have a graph here. Yeah. You can make a graph where you plot the pressure. Well, this is pressure and temperature, but you could have done, like I said, the volume and temperature if you keep it at constant pressure. And you extrapolate back, and it comes to a point where no matter what you started with, the line is going to hit zero pressure, zero volume, at a temperature of minus 273.15 degrees Celsius. So, absolute zero is minus 273.15 degrees Celsius. Now, there's also a Fahrenheit. I don't remember what the number is because in science we don't use Fahrenheit. And so why would you worry about it? Because absolute zero is really only going to come up in science. And so we have a new temperature scale that's called the Kelvin scale, named after Lord Kelvin. And the Kelvin scale is what we call an absolute temperature scale. I'm guessing that's why there were the two people who said yes, but only for Kelvin. Because the Kelvin scale is an absolute scale, which means 0 Kelvin is absolute zero. And the Kelvin scale is simply based on the Celsius scale, but with an offset of that 273.15. So the Kelvin temperature is just the Celsius temperature plus 273.15. So if you know Celsius, you know Kelvin. This Kelvin one is the one that actually allows us to determine if we've doubled the temperature. So if you go from room temperature is 291 kelvins. No, not 291, 293 kelvins. So room temperature equals 293 kelvins. We don't use a degree sign with kelvins, by the way. It's just a K by itself. If you're going to double the temperature, that's 20 degrees Celsius, 68 degrees Fahrenheit, or 273 kelvins. If you're going to double the temperature, which one of those numbers do you double? The kelvins. So doubling room temperature takes you up to 586 kelvins. Or converting that back to Celsius, that's going to be 313 Celsius degrees. Obviously very hot. So we can talk about doubling the temperature, but we have to use kelvins if we're going to talk about doubling the temperature and double the number. That was a lot of talk for can we double the temperature. But of course, it covers some important things. It cannot get colder than 0 kelvins. Why not? Okay, what did you say, Andy?
There's no more energy, like, I guess.
Yeah, you've already stopped it. You can't slow it anymore.
Can't go negative.
Now, just something else that will never show up on a test. Don't put it on your potential test question. Theoretically, we can create negative temperatures. It's just negative temperatures are hotter than infinite temperatures. You can see why it's theoretical. You can do this because temperature is actually defined in a very interesting manner in physics. And so by having states in a certain way, you can make it so you have a negative temperature. But yeah, it would be violently hot. If you put your hand on a negative temperature object, it would obviously incinerate you. So that's just, it's a funny curiosity thing. So if you ever see an article about negative temperatures, it's possible it's just a really hot temperature. It's not a colder than 0 temperature. Because you can't get colder than absolute 0. So the wording here, can anything get colder than absolute 0, is still correct, even though you could have a negative temperature because that negative temperature is hotter. Can it be reached? The answer to that question is also no. The third law of thermodynamics. Now, we have laws of thermodynamics. We have the 0th law. Who remembers the 0th law of thermodynamics? Who remembers we had school 1 week ago? Well, 1 week and 3 days ago. Well, yes, not Andrew. Andrew's all, I'm out of this conversation. But we did have school back in the long ago. That's a South Park reference, by the way. The long ago turned out to be a week ago. We did have school, and we did have the 0th law of thermodynamics, which said that if object A is in thermal equilibrium with object B, and object B is in thermal equilibrium with object C, then object A is in thermal equilibrium with object C. Thermal equilibrium. What did it mean for two things to be in thermal equilibrium?
I'm guessing they neither transfer or move heat.
You weren't even here for that, and you guessed right. For two things to be in thermal equilibrium, if I bring them into thermal contact, so essentially if I make them touch each other, no heat flows between them. Since heat always flows from the hotter or higher temperature to the lower temperature, if I bring them into thermal contact and no heat flows, they must be the same temperature. So thermal equilibrium is a complicated way of saying the same temperature. But then once you understand that, you go back and you look at the words I said. I could have said, if temperature A equals temperature B and temperature B equals temperature C, then temperature A equals temperature C. And you'd say, well, no kidding. You know, if these coins are the same value as these coins, and these coins are the same value as this bill, then this bill is the same value as the first set of coins. Right? It's very basic. It's the zeroth law, because they thought temperature was that simple when they started studying thermodynamics, and then when they got to these more complicated understandings of what temperature was, the things that allow you to make a negative number for temperature, they realized that it wasn't obvious like they thought it was initially, but they already had the first law of thermodynamics, which is that energy cannot be created or destroyed, and they had the second law of thermodynamics, one of which statement says that heat always flows from the hotter object to the colder object. They said this is more fundamental than those two, so they call it the zeroth law, to get that most fundamental one first. The third law of thermodynamics says that nothing can have a temperature below absolute zero. And so we have the third law, nothing can have temperature below absolute zero, and in fact, nothing can reach absolute zero because basically, how do you get something colder?
Put it next to something.
Put something next to something that's colder. And then heat will flow out of the colder thing into the warmer thing, making it cooler. But if I can have nothing below absolute zero, then what colder object can I use to bring something down to absolute zero? Nothing. And so we can't even reach absolute zero. Now, physicists have figured out very tricky ways using lasers to slow particles down so they can get very close to absolute zero, like 0.0001 kelvins. Most of us would say, close enough. But a physicist says, but it's not there. And in fact, I can never get there, but maybe I can move it out another decimal place and that would be cool. I can't believe I've already used up half my time. All right. Let's talk about this funny thing called specific heat capacity. If I have heat that flows from a hotter object to a colder object, what happens to the temperature of the hotter object? It's going to drop. And we can explain that using our understanding that temperature is a measurement proportional to the average kinetic energy. If work goes out, work is energy. And so if work went out, the energy had to drop, which means the average kinetic energy had to drop if you didn't have molecules leaving. Average kinetic energy drops, means it got cooler. And so it makes perfect sense. But how much does the temperature change when you remove heat? That depends on the material. If you have water, it's going to change a lot differently than if you have, let's say, wood. Take the same amount of heat out of wood, its temperature will change a lot more than the water will if you take the same amount of heat out of the water. And so this specific heat capacity is a number that tells us about how the temperature changes if we remove heat. And so we have a basic relationship. We use the symbol Q for heat. M is the mass of whatever our material is that heat is being added to or removed from. C is the specific heat capacity. Very often we don't say capacity with that, we just say specific heat. And then we have delta T. So this specific heat tells us how temperature relates to the heat. So I think I better go to the next slide before I say something and then come to the next slide and say, ah, here it is. See, I knew it was there. That's our basic equation that I'm sure is going to be on a slide coming up. Not this one, though. Oh, wait, no, it did have something important on it. Oh, no, forget it. I just saw the 100 and was thinking about that. Back with the earliest theory, at least the earliest modern theory on heat, the idea was that we had the caloric and the frigidic. The caloric was a fluid that would flow and make things hotter. The frigidic, a fluid that would flow and make things cooler. These days, we completely forget about that whole frigidic term and just talk about calories. Calories were measurements of this fluid that was flowing for heat. And so the calorie was defined based on water. That is, 1 calorie is the amount of heat necessary to raise 1 gram of water by 1 degree Celsius. Now, I probably have no, I don't have the more specific. It turns out temperature does matter, so the very strict definition of a calorie is the amount of heat required to raise 1 gram of water from 14.5 degrees Celsius to 15.5 degrees Celsius. That's the strict definition of a calorie. But a calorie is an amount of heat required to raise water by 1 degree Celsius. So that means for water, remember Q equals MC delta T, it's written up above. For water, we know if I have 1 calorie for Q, and if I have 1 gram for mass, then the change in temperature is 1 degree Celsius. That's how we defined the calorie. And so I can immediately calculate what the specific heat of water is. The specific heat of water must be one calorie per gram degree Celsius. And actually, I'm going to put Celsius degree. If you put the degree sign after, it means a change in temperature. If you put it in front, it means a temperature. That's a technicality, again, that I am not going to hold you accountable for. Don't put that on your potential test question either. So the specific heat of water is 1 calorie per gram degree Celsius. That's where the calories come from. Now, let's say that I'm on a diet, because I really should be, right? If I'm on a diet in America, I count my calories. It really is the same thing. A dietary calorie is only different from this calorie by one little itty-bitty thing. One dietary calorie, which we write as 1 capital C calorie, is equal to 1 kilocalorie. That is, a dietary calorie is 1,000 calories. So if I eat a chocolate bar and it says it has 220 calories, that means it has 220,000 of the calories we talk about in physics. So the energy contained in that chocolate bar could raise, 1 gram of water by 220,000 degrees Celsius? That's a lot of energy, right? Now you're wondering, how do they get those numbers? What do you do with a witch? You burn her! And that's how they get these as well. They burn the food, and they measure how much heat is produced, and that's how they determine the calories in it. So they have things that are called a bomb calorimeter. They take this little container and they put in there a little filament that's going to make it burn, and a pure oxygen environment so anything will burn. And then they put it in a water vat, and then they put a little electricity through that filament so it starts it on fire and it burns, and it's a strong thing. It's called a bomb calorimeter because when it burns it gets really hot. The pressure goes up. If it's not strong enough, it will blow up, right? So it's got to be strong. And then they measure how much heat flows from that little bomb calorimeter into the water, and they say, that's how many calories were in the food. So it's all related. Now, if we lived in, let's say, Australia, right? You always wear that hat that makes me think Australia. If you look on your Coke can, instead of saying it has, 2,000 calories per sip, it says how many kilojoules. Right? They actually just measure it in joules, the standard unit of energy. Because heat is a transfer of energy, so the calorie has to be related directly to joules of energy. So when we do this, we call this work here calorimetry, measuring the relationship between temperature and heat. You can use either calories for units of heat or joules for units of heat, because they're both units of energy. Okay, I've spent plenty of time on that. There's another really important thing that I can't forget on it, so if it's not, okay. This here is a question for you to solve. If the specific heat capacity of ice is 0.5 calories per gram degrees Celsius, which is true, by the way, how much heat would have to be added to 200 grams of ice initially at minus 10 degrees to raise ice to its melting point? Quick question, what's the melting point for ice? 0, right? I don't want to be tricky here. So you're going from minus 10 degrees to 0 degrees. How much heat do you have to add if the specific heat is 0.5 calories per gram degree Celsius? Waiting for one still. Bueno. Okay, so the answers, okay, it's still, there we go. The answers people put in were 6, 1, 1, and 0. Now 6 people agreed, and those 6 people are right, but let's go through how they got that for the other 2. Or some of those 6 may have guessed as well. That's always an option. So we know our relationship Q equals mc delta T. And we're looking for Q, so I'm just going to put in my mass. My mass was 200 grams. My specific heat, which was 0.5 calories per gram degrees Celsius. And then my change in temperature. Change in temperature is always the temperature final minus the temperature initial. My initial was minus 10 degrees Celsius, and my final was 0 degree. Very nice. Final was 0 degrees Celsius. That's going to be 0 degrees Celsius minus a negative 10 degrees Celsius. Of course, 0 minus negative 10 is plus 10, right? 10 times 200 times 0.5. 200 times 0.5 is 100, right? Half of 200 is 100. Times 10 is 1,000. So that was 1,000 calories. Everybody see how that worked out? Excellent. I think I have another clicker question here. Nope, not yet. Phase change. Before I talk about the phase change, I want to talk about one more important thing with specific heat. The specific heat of water is quite high compared to specific heats of other materials. Now, in terms of that equation, Q equals mc delta T, I like to look at this and say, well, how does temperature change relate? So, not relate to the slide here, but to the previous slide. If Q is equal to mc delta T, then delta T is equal to Q over mc. So if I have water that has a large C, a large specific heat, if I put a bunch of heat into it, will I have a bigger or smaller change in temperature than if I had something like aluminum that has just a little bit more than 1/5 the specific heat of water? If aluminum has a smaller C, what does that make its change in temperature? bigger. So water will change temperature much less than other materials when you add heat or remove heat. That's really important. You know I'm from California. We have a big ocean called the Pacific Ocean. And since that ocean is made of water, that ocean has a large specific heat. Now that water comes down from Alaska. So you know what that water temperature is? It's pretty chill. Where I grew up as a kid, you go out in that water and it's like 50 degrees Celsius. Celsius, that would be really hot. 50 degrees Fahrenheit. Well, what does that do? That's going to make it so when the sun is shining bright over the land heats up quickly and gets hotter. It heats up the air above it. That air comes over to the ocean, goes into the ocean. That heat just barely raises the temperature of the water. And as a result, it has a cooling effect. So near the ocean, the temperature doesn't change very much, and it stays much cooler during the hot summer days. So where I grew up, Monterey Bay County, right there on the beach, the highest it ever got was like 85 Fahrenheit. It never got hotter than that. Now you go inland, you go like 2 miles inland, it might get up into the mid-90s. But right there next to the water, it stayed much cooler because we had that big body of water. And of course, in the winter, out here in the middle of nowhere, we don't have any water around us. We don't get that radiation from the sun very much in the winter, and it gets really cold. But out there in California, if you're on the coast like I was, that water is going to warm up the air. And so the coldest it ever got was around maybe 40 degrees Fahrenheit. It was usually between 60 and 75. Just think about that for a minute. I grew up with the temperature pretty much every day. It's either going to be bitterly cold at 60 or super hot at 75. It's pretty good times. Part of the reason we love our California. My sister lives in Huntington Beach. She's about a mile from the ocean. So once again, her temperatures rarely get hot, never get cold. But if you stay right there and you go another 10 miles inland, it'll get baking hot because you're farther away from that water. It's a very important thing about the water. It helps us stabilize temperatures. It's what makes living on the coast nice. Okay, another clicker question for you. I got to get here. If specific heat capacity of ice is a half a calorie per gram degree Celsius. Oh, wait, don't answer yet. I didn't talk about the previous slide, did I? No. And this question here requires that I talk about that slide. When you change phase, remember when I talked about the simple common phases of matter, solid, liquid, and gas. The solid, the molecules were bound in a specific position that they can vibrate. You increase the temperature, they're vibrating faster. They have more energy in their vibrations. Until you increase the temperature enough that the added energy you put in makes them break loose. And that's what we call melting. So when you have something melting, you put in heat, and instead of that heat making it move faster, that heat allows it to break free. And so the heating doesn't increase the temperature when it's melting. It simply liberates it, allows the material to break free and melt. So during a melting process, the temperature doesn't change in a pure material. The temperature doesn't change during melting. Impurities, there is a change. So in physics, we just talk about pure materials. Temperature is constant during melting, and the amount of heat you put in is proportional to the amount of material that's going to melt. So in this equation, m is the mass of melted material. So I might start with the block that's 100 grams of ice. If I melt 50 grams, then the m is going to be that 50 grams I melted, not the entire 100 grams I started with. If I melt the entire thing, then m would be the 100 grams. So m is the amount of melted material. L we call the latent heat. If it's melting, it's the latent heat of fusion. Why fusion? Well, turn melting the other direction, it's freezing. If you remove the heat, it freezes and you have the same relationship for how much material was frozen. And so that's where we have the latent heat of fusion. If you cause something to vaporize, then we have the latent heat of vaporization. It's still this equation, but it becomes the latent heat of vaporization if you're causing something to evaporate. So the heat simply is the mass times the latent heat. The mass that was changed from one state to another times the latent heat. So with that, now we can answer this question. And good, no one answered it without having the discussion. So we have this ice that has heat capacity of 0.5 calories per gram degree Celsius, a latent heat of fusion of 80 calories per gram. How much heat would have to be added to the 200 grams of ice initially at minus 10 degrees Celsius to completely melt it? That's good because this is a more difficult question than it seems at face value. Actually, the lines don't match up. I assume you got it correct. Okay, we're all in. And here's what we have. 0, 2, 5, 1. Now, like I said, it put it on a different line, so I've got to check and make sure if you're right or not rather than saying, yeah. What was the tricky thing about this question? You weren't starting at 0. You were starting at minus 10 degrees Celsius. So the first thing you had to do was heat it up to 0. So we have Q1. If it's heating, that's going to be the MC delta T. We just did that calculation on the last clicker question. That was 200 grams times 0.5 calories per gram degree Celsius times 10 degrees Celsius, which was 1,000 calories. But then we have the second part. So what's the second part that we have in this problem? We have to melt it, so we have the ml. And so then I'm going to have my 80 calories per, whoops, I put L first. My 200 grams times 80 calories per gram. Well, 2 times 8 is 16. So that's 1,600 calories. So the Q is Q1 plus Q2, which is going to be 1,000 calories plus 1,600 calories. You're right. $200 times 10 is 1,000. Thank you. I don't like my math to not work. So, only one person got the correct answer here. 5 people got the 16,000 correct, but forgot to add the 1,000. So that was a little more involved. And sadly, we're a little out of time. I'll see you in lab this afternoon where we'll be doing an experiment. Oh, anybody want your books now? If you want them, I can give them to you right now if you just go with me to my office.